Welcome, students, to this second screencast of Module 6, in which we will discuss separators and the concepts of tortuosity and porosity. Let's start with the separators. As the name already suggests, separators separate the analyte from the catalyte. Typically, they are membranes. Well, separators have a number of different functions. The first one is that they enable ion transport between the analyte and the catalyte. That is essential. If a separator does not allow ion transport, an electrochemical system cannot function. Secondly, a very useful property of the separator is that it enables the anode and the cathode to be put very close to each other. A separator typically is only a couple of 100 or 200 micrometers thick, and you can push the electrodes against that separator. So you actually have quite a small distance between the anode and the cathode. Without a separator, it's not possible to operate with such a small distance, because there's just a very high risk that the electrodes will touch each other, especially for the somewhat larger cells. Then the third function of the separator is to prevent any mixing of gases. Often in electrochemical systems, we form gases at both the anode and the cathode, and often these gases, when they would mix with each other, they could form an explosive mixture. So the separator actually helps keeping the gases apart. Now the fourth function, still worthwhile mentioning, is that it also enables the use of different analyte and catalyte uh, compositions. And that is useful for particular electrochemical systems where that is desired. There are different types of separators, as you can see here. However, for electrochemical systems, only two of them are really relevant, namely the microporous separators, which you can see here. They basically consist of a porous structure consisting of a solid material, and then pores, which are filled by the electrolyte. The other type of separator we often see is the electrically charged membrane. Here you have very small pores in the nanometer range, and in the pores you have charged groups that affect the ion selectivity of the membrane, which we will discuss further in the next slide. These electrically charged membranes are also known as ion exchange membranes. Within them, they have these charge groups. It can be either negative or positive. An often occurring negative group is the sulfonate group, and an often occurring positive group is a quaternary ammonium group. Well, if you have a membrane with these negatively charged groups, it's known as a cation exchange membrane. Now, why is that the case? So you have the negative charge groups, and they interact with ions that are also in the membrane. They actually attract positive ions and they repel negative ions. So what does that mean? If you now look at the membrane, you can see it here on the right. You have a positive ion, basically, it's attracted by the negative sulfonate group. And it's actually able to hop basically from one negative sulfonate group to the next. And in this way, it can pass through the membrane. However, negative ions that try to pass through the membrane are repelled by the sulfonate groups. And because of that, they cannot really get to the membrane, or at least quite difficult. So that's why it's called a cation exchange membrane. It favors cation transport over anion transport because of the charged negative groups. For the anion exchange membrane, it's the exact opposite, because there you have the positive charge groups, so the positive ions are repelled and the anions are attracted. So that enables you to achieve selective transport of anions. A special type of ion exchange membranes is the bipolar membrane. A bipolar membrane combines an anion exchange membrane with a cation exchange membrane, basically put them on top of each other. Now, if you put it in the right way in relation to the positive and the negative electrode, you can see that ions cannot travel through it because a positive ion that wants to move to the negative electrode is blocked by the fact that there is an anion exchange membrane here, which does not allow for the transport of cations. Negative ions that want to move towards the positive electrode are blocked by the cation exchange membrane layer. So the only way this membrane can transport ions is by splitting water. So water, because it's not charged, can diffuse into the membrane from both sides. And then in the middle of the membrane, it's split into OH minus and H plus. The H plus can move towards the cation exchange membrane towards the negative electrode. And the OH minus can go through the anion exchange membrane towards the positive electrode. In this way, a bipolar membrane allows you to split water without having to generate hydrogen and oxygen. So it's a very useful membrane if you want to change the pH of a solution. Key properties of an ion exchange membrane are the perm selectivity and the conductivity. The perm selectivity indicates how selective the membrane are. For example, if we have a cation exchange membrane that has a perm selectivity of about 93%, it means that 93% of the current is transported by cations, whereas 7% of the current is transported by anions. If it would be an anion exchange membrane, it would be the exact opposite. So it really indicates the selectivity of the membrane. The conductivity indicates how conductive the membrane is. And obviously you want to have as high as a conductivity as possible because you want to minimize the ohmic resistance in the electrochemical system. Now you can see here that we have to make a trade-off because typically the higher the conductivity, the lower the selectivity. Of course there are exceptions, but that is the general rule. We can also see that the conductivity increases with increased water uptake. So the higher the water uptake into the membrane, the higher the conductivity, but hence also the lower the perm selectivity. So we can play around with membranes to get them to the desired properties, but we typically need to make some kind of trade-off. Now we have discussed ion exchange membranes, it's time to discuss porous structures. And these porous structures can be either separators, but they can also be electrodes. That depends on the solid material they are made of. If this solid material is a conductive metal, it might be a very suitable electrode material. If on the other hand it's a non-conductive material, then it might be perfect for a separator. In any case, these porous materials have some key properties, namely the tortuosity and the porosity. And together they, for example, determine the conductivity of the material. But they also influence, for example, the resistance to gas crossover or ion crossover. So these tortuosity and porosity are key properties. Now, let me briefly introduce them. The tortuosity, or in Dutch kronkeligheid, basically indicates the path length which ions need to travel to get from one side of the separator to the next. And basically you can see that here. This is the path length, and you can see this path length is significantly longer than this distance y. So the tortuosity is x divided by y, and it's always larger than 1. The porosity indicates the pore volume of the electrolyte compared to the total volume, and that one is always smaller than 1. Just to clarify it a bit further, here you have a membrane with a single pore which has exactly the same length as the membrane thickness, and then in that case you would have a tortuosity of 1. This is very rare. For example, for this pore, the tortuosity is about 1.5, and for this typical, more complex structures, tortuosities typically range between 1.5 and 2.5. Now, I would recommend you to now carry out quiz question 6.3 to practice a bit yourself with this concept. The next concept I would like to introduce is specific interfacial area. This indicates the ratio between the surface area inside the porous medium divided by its volume. So you see here a porous material, and basically you take the surface area of all the material that's inside, so of all these particles, and you divide it by the total volume. And so what you see here, so the interfacial area divided by what we call then the superficial volume, and you see that then you have square meters divided by cubic meters. So this the unit of the specific interfacial area is 1 per meter. What can sometimes be a bit confusing with these porous materials is what current density means. Is the current density per square meter of area, or is it really this current density at the electrode material? Now, for that we have 2 types of current density, namely the geometric current density, where we just say if this is 1 square meter, then we put in a certain current, and then is that current per square meter. And we have the real current density, where we really look at what is the current density at the electrode surface. Now these 2 you can connect together via this equation. So the real current density is the geometric current density divided by the interfacial area and divided by this length d. And you need that because A and D together, that's dimensionless. So you need to have this length d included. So it's important to mention that in electrochemistry we typically use the geometric current density, but if you really want to understand the electrocatalytic properties of a material, it's good to convert the geometric current density towards the real current density at the electrode material.